Welcome to the financial math lesson on progressions. In this lesson, I'm going to talk about arithmetic progressions, geometric progressions, and other types of progressions. We'll be using the general ideas here in the following lessons related to simple and compound interest. On this slide, I'm going to talk about the simplest case, arithmetic progressions, and that is the case where you start with a number, could be a whole number or a fraction, and you add the same amount to it each time. So I'm showing an example here. You start with 1 and then you add 3. So your difference, it's called the difference, is 3. You can see here how that works. And you can also have a negative difference. So here you go from 10 to 5 to 0 and minus 5, minus 10. The third example shows that you can start with a minus number, a negative number, and you can also have a difference of a decimal. So you have minus 0.125 plus 0.25, and that gives you plus 0.125, and then plus 0.375, and so on. So the general pattern is it's the first term, then the first term plus the difference, then the first term plus twice the difference, and so on. And so the nth term is the first term plus n minus 1 times the difference. We can also compute the sum using a trick. We list we call it S sub n, and we list the first n terms here. So x1, x1 plus d, and so forth, and this is x sub n, and then this would be x sub n minus d, and going in this direction. And then we just reverse the order, and so it's the same sum here, but in the opposite order. Then when we add these together, you notice we get x sub 1 plus x sub n, and you get the same thing again because the d's cancel out, and then the two d's cancel out, and you get again x sub 1, x sub n, and that's true all the way down. So n times you get x sub 1 plus x sub n, and that equals 2 times the sum s sub n. And then to find s sub n, we just divide both sides by 2, and we get this formula here. Geometric progressions are very similar to arithmetic, except you multiply instead of add. You can see here the first example I have. First term is 3, but we multiply by 5. That's our common multiple to get the subsequent terms. Then in this example here, the second example, we have a negative, which is fine. We start with a negative term, and then we're multiplying by a negative. So you would get 1.25, and then when you multiply that by minus 0.125, you get a negative. When you multiply this by minus 0.125, you get a positive. So whenever you have a negative common multiple, the progression alternates. The general format is shown here. A is the first term, then a times the common multiple r is the second, and then a times r squared, and so on. The nth term would be a times r to the n minus 1. We can also develop a formula for the sum of the first n terms, which I've written out here. This is the sum. And if you multiply this by r, you get this expression here. And if you subtract these two, you get a lot of cancellation. You notice the ARs cancel the AR squares. The only thing left is a minus a times r to the n. So you get this here. Then you factor in s sub n out of this. So it'll be s sub n times 1 minus r. And you divide that into both sides, and you get this here. So that's your formula for the sum of the first n terms. And you can multiply the top and bottom by minus 1 to get this equivalent expression here. So sometimes we'll use this, and sometimes we use this version. I have an example of our formula for the sum of a geometric series here. We want to find the first 5 terms, or the sum of the first 5 terms, I should say. And the multiplier is 2, and the initial term is 100. So we just plug in A equals 100 and R equals 2, which I've done here. You get 100 times minus 31, but then the denominator is minus 1. So you get minus 1 times 100 times minus 31, you get 3100. In the case where R is between 1 and minus 1, if you want it, you can sum up all the terms from up n equals infinity in that case, which I've shown here. And what happens is this R to the n term goes to 0. Whenever R is between minus 1 and 1, and you keep raising it to higher powers, for example, if R is 1/10 and you raise it to the 5th power, you're going to get 1 over 10 to the 5th. So it's already almost 0, but as you go out to infinity, this term becomes 0, and you just get this formula here. So this is kind of neat because it allows you to sum an infinite series. I've shown an example here. We have 2 as the first term and 1/3 is the multiplier. So you get 2, 2/3, 2 over 3 squared, 2 over 3 cubed, and so forth. And then since R is between 1 and minus 1, it's 1/3 in this case, you can use this formula and you put in A equals 2, that's the first term, and then the multiplier is 1/3, and you just get 2 divided by 2/3, which is 3. So there are other types of progressions. We're not going to need those for our work in financial mathematics, but just for completeness, I have a few examples on this slide here. So a recursive progression is a progression in which each term is defined using one or more of the previous terms where the first several terms are given. So I have an example here where an, the nth term, is the sum of the previous two terms. And we're given that a1 and a2 are both equal to 1. So these are the first two terms. This is known as the Fibonacci sequence. It's very common in mathematics to see this in a lot of different places. So you see here the first two terms are 1, and then we use our formula here. The third term is the sum of the two before it, and then the fourth term is the sum of 1 plus 2. This term here, 5, is the sum of 2 and 3, 8, 3 and 5, and so forth. And you get this series here. Then there's another less common recursive progression. It's called the Tetranacci numbers, which start with the first four terms being given. So A1, A2, A3 equals 0, and A4 equals 1. So I've written them up here. And then the formula after that is that A sub n equals the sum of the previous four terms, unlike this where we just did the sum of the previous two. So you notice here we have the first four, then this is the sum of those four before it. Then 2 is the sum of these four that I'm pointing to, and then 4 would be these. Then this would be the sum of these four terms here. That's 8, then 15. So it's a little bit quite different, I should say, from the Fibonacci sequence. And I just have a remark here, which I already mentioned. I just put them here for completeness, but we're not going to need these beyond this one example slide that I'm giving you. We will have just mainly geometric progressions and arithmetic progressions when we talk about financial mathematics in the following lessons. I wrote 2 Python programs in support of this lesson. The first program has this name here. It's the name of the file, and that computes arithmetic progressions. The second program computes geometric progressions, and the location is here. I'll give you the link in the information, so you don't need to copy that down. But when you go to this place on GitHub, you'll see a bunch of programs, and you just want to look for these two now. Future lessons, there'll be other programs that I'll refer to. It'll be at the same link here. So I'm not going to give you a walkthrough of the code, but you're welcome to use that and change it and however you like. And what I will do is run the code, which will present a user interface for each one of these, and then I'll do a few examples. So on the next slide, I'll do some examples of this arithmetic progression program. Then on the slide after that, I'll show you some examples of the geometric progression program. What I'm showing here is the arithmetic progression program that I wrote in Python. This is the GUI for the program. So you put in the initial term, say 2, then the step length, let's say 3, and then you can put in a number of terms you want, 15. Then you have a choice here. You can either just calculate the 15th term, or you can generate the progression and show its sum. So let's do this option here. So you see that it generated the sequence. So we started with 2, and then we added 3, 3, 3, and so forth. And then it added up all the numbers. And then we can clear that and do another example. Let's start with a -7 and a step length of, 45. And let's say we wanted to know the term 10,000. So we don't really want to print all these out, but it would be nice to get maybe just the nth term, the 10,000th term in this sequence. So we can use this option here. And that's the 10,000th term in this sequence, and we can clear that. We can do another example if we like, or when you're done, you can just hit quit. This is the second program I wrote for this lesson. This one does geometric progressions. It has a very similar format here. You put in the initial term. Let's try something easy, 2. Common ratio, 3. And let's go for 15 terms. We can either generate the progression in its sum or just the 15th term in the progression. So let's do this one here. So now I've used a little bit different format. You notice I have a scroll bar here, but you can see it's the same idea. You have 2, and then 3 times 2 is 6, 3 times 6 is 18, and so on. And then this is the sum of all these terms. We can clear that. We can start with another one. Let's start with 4, and let's do a ratio of 1.5. Let's say we want 33 terms. And in this case, we'll just generate term number 33. So we'll hit this button here. And you get that. And then we can clear it. And again, if you can continue and play with other things here, you might want to try using a negative common ratio, and you'll see that you get an alternating series. And then when you're done, you just quit it. I conclude this lesson with some exercises. If you want to try them without any of the extra information I'm going to give you in a second, you may want to just pause the video here and take a screen capture of the slide. Otherwise, I'm going to go forward and kind of give you some hints in addition to the hints that are already written there. So the first one, show that the sum of an arithmetic progression can also be represented by this equation here. And this is pretty easy. You just take your equation for S sub n that we derived earlier, and then we also had a formula for x sub n, and you would plug that into this, and you would get this formula here. Second question or exercise, find the term number 335 in this progression here. So we can see that the first term is 3, and then we're adding 6, so the difference is 6. And you can use the Python program that I just described a couple of slides ago to do that. Then we have one going a little bit differently here. If the 57th term in a arithmetic progression is 677, and we're told that the difference is 12, what is the first term? So we can solve the equation for the nth term of an arithmetic progression and basically solve for x sub 1, or we could do it via calculations using the Python program that I provided. So you would take 677 as the initial term, and then rather than 12, you would take minus 12, just counting back 57 terms, and that would give you the answer also. So you may want to try doing that both ways. The next problem, find the 237th term in the geometric progression with an initial term of 2 and multiplier 1 by 1. And the hint is to use the Python program I provided on geometric progressions. Then the next one is find the sum of the first 10 terms in the geometric progression with initial term 25 and multiplier 7. And you can also do that with our program on geometric progressions. Problem number 6, if the 8th term in a geometric progression is this number here, 2,470,629, and the multiplier is 7, what is the first term? And I just wrote down here, this is the equation for the 8th term. And we're told it's this number here, and then the equation is a times the 7, the multiplier, times n minus 1, so it'll be 8 minus 1. And so all you need to do is raise 7 to the 7th power. You can do that on a calculator and then divide it to here and solve for a. And then finally I have another progression that kind of fits the model that we had talked about with the Fibonacci numbers. We're given, it's called the Lucas progression. It's 2, 1, 3, 4, 7, 11, 18. And the question is, what's the formula? And I guess I would ask you also to say, what's the next term? Once you figure out the formula, you could pretty much predict that. And it's very similar to the Fibonacci. You notice we're given, if you take the 2 and the 1 and you add those, you get 3. If you take the 1 and the 3, you get 4. 3 and 4 is 7. 7 and 11 is 18. And so the term after here would be 29. Okay, so that was the last slide in this lesson. And as I say, this is kind of background information. The following lesson, I'm going to talk about interest rates, and we'll use some of the ideas from this lesson to help us understand how to do various calculations with interest rates.